acid and bases 4, here we go. Now, when we think about these old AP problems, we want to think about where do we see equilibrium problems, where do we see titration-driven problems, and where possibly could there be that buffer scenario where we have conjugate and acid and base both present, where we can use the Henderson-Hasselbalch equation. Any case, let's get started. So propanoic acid, here we go, H in front, screaming to you that it gives off an H, ionizes in water, which means it makes ions. That's why there are electrolytes. Okay, breaks apart into ions, according to the equation above. Now, people say, oh, is this a strong acid, weak acid? Well, my friends, in chemistry, look at the Ka. It's tiny. What does that scream to you? That it barely goes forward. This is the dissociated or the undissociated acid, and here's the conjugate base. The Ka is favoring, okay, the undissociated acid. It barely goes forward, which means that Kb in the reverse is a little bigger. So let's go on and do the constant expression. So it's products over reactants, coefficients become exponents, and solids and liquids do not apply. So our Ka, I keep saying KSP because we've done that already, is equal to the products, and that's C3H5O2. That's the conjugate base, what's left over after the acid gives off. And then we have the proton, which is synonymous with H3O+. And we get rid of, on the bottom, products of reactants. So here's our reactant. It's aqueous, right? So HC3H5, and this is the conjugate acid, O2. And my gosh, there's a point right there. Okay, no big deal. Now here comes the big deal. They want the pH of a 2.65 molar solution of propanoic acid. Now it's not really a big deal, but the deal here is that they want the pH. Now what's the pH? The pH is the negative log of the concentration of my H+. So I need the concentration of the H+. Now this would be easy if it was a strong acid. Whatever the concentration of my acid is, that would have to be the concentration of the proton. But because it's sitting in water, aqueous, and because it's weak, it's going to reach equilibrium. And so let's write it. Let's write the conjugate acid, HC3H5O2, double arrow, equilibrium style, C3H5O2 negative plus the H plus. All right. Now let's write our ice table. It's an equilibrium problem. So we're going to have initial, change, and at equilibrium. And that's usually what we're after, is at the equilibrium. Now, what do they have here? Well, they had a 0.265 molar. Now, equilibrium problems are in molarities because we're using these brackets right here, which are molarities, and they gave us 0.265 molar of the acid initially. So let's write it, 0.265. Okay. Now, what's going to happen here is that we're going to have no conjugate base and no acid. And that's not really true if it's sitting in water, but we're always going to take the position that we're going to start at this position. We're 100% HA. So let's pretend we're starting with HA completely, okay, undissociated. Because that Q is going to be what? Less than K. If I assume I'm at this position, it's going to go forward somewhat. Okay, and that little arrow somewhat means that this is going to be minus X. Okay, this is going to be plus X, and this is plus X. And the reason is stoichiometrically it's a 1-to-1-to-1 ratio. And at equilibrium, this is what we're really after, 0.65 minus X, and X plus 0. To do that math, I can do that in my head, okay? And there's my values. Now, because they gave me the value of Ka, I can solve for X. So when we do KSP problems and they give me the KSP, I can solve for the value of the concentration of one of my products. Now, in this case, I can solve for this X. Now, one little issue here, which is not a big deal, this X is barely going forward. We're going to go forward a tiny bit because Ka is really small. That means not a lot of products are favored. So compared to this big number, and it may seem small, but it really is big compared to how much X disappears, this X will be insignificant. So we're going to approximate that away, and we're allowed to do that, okay? And it keeps away the quadratic catastrophe. So what we have is Ka, I know I want to keep saying it, is 1.34 times 10 to the negative 5. And it's equal to, guess what? X times x. Remember, this is the x in here, so that becomes x squared. All over 0.265. All right, so all I've got to do algebraically is take 1.34 times 10 to the negative 5, and then I'm going to times it algebraically by it should be 6.5, but hey, I'm tall, 0.265 molar. And of course, because that's equal to x squared, we're going to square root both sides. And that's going to give me x in my later of calc. And when I do the math, I get x equal to 1.88 times 10 to the negative 3. Okay, and what did we find? We found the concentration of either the conjugate base or the proton. But since they're after the pH, we need the H plus ion concentration at equilibrium. So we found this. We found it. And now we found the concentration of the H plus. So in order to get our pH, we've got a little p means negative log. We've got to negative log it. So do the negative log of 1.88 times 10 negative 3. And again, if this is new to you, I'm just going to go negative log in my calculator of this number, 1.88 times 10 to the negative 3. And when I use that handy dandy calculator, okay, and do the negative log, I get a pH of 2.74. So my pH is equal to 2.74. And I'm looking at my Ka, that gave me 3 sig figs. There's no other number there, so I'm going to end up with 3 sig figs. And that is how I do it. And that's an equilibrium problem. And we're sitting in water. How do I know? I see the aqueous here. All right, and I had to know how much we went forward because the reverse is also happening. Important you see that. So let's move on to the next part. Now this isn't as clear as some people might think. Now in this part, I'm going to add 0.496 grams of sodium propionate. What the heck is that? If they're adding something, just like KSP, as I keep kind of saying in class, if I have a solution that's saturated with ions and I have the ions dissociating and dissolving as fast as they're precipitating in a saturated solution, if I add a common ion, it makes things happen. Well, we're adding a common ion. This sodium, okay, propanoate, you should recognize is going to break apart into the sodium ion, which we know is of course a spectator, and then the what? H5O2 negative. This should look familiar. Well, if you look very carefully, isn't that this? Isn't that the conjugate base of propanoic acid? So what we're going to do is take a solution, okay, of 0.65 molar propanoic acid, which we just worked with in the same question above here to find its pH, and now we're going to essentially add some conjugate base to the mix. So we're going to add, along with this, we're going to have some conjugate base. We have a buffer party, people. Now, before we can get to our fun calculations, we got to look to see what's the molarity, because remember, all these equilibrium problems are based on molarity concentrations of what? Aqueous and gases, because solids and liquids do not apply. So I'm going to start with 0.496, and I have grams, and what I'm going to have to do is I'm going to have to convert it to moles, because molarity is a mole over a liter. And we have this the volume, okay? So assuming, of course, there's no change in volume when I add those grams. So the first thing is get rid of the grams. What's the gram form of the mass? One mole is equal to how many grams? Well, I have to go to my periodic table. And when I do so, I have 3 carbons, and 3 times 12 is 36. 5 times the mass of 1H is 5, and I'm rounding off to my heart's content. And then 2 times 16 is 32. And I can't forget that this is the mass of the sodium propanoate, so that's 23, 1 times 23. And when you do all of that, okay, and correctly, because sometimes I make mistakes, you get 96. So that equals 96, and that's grams per mole. So let's get rid of that work. I don't think we need that there. So we get rid of that work. And then back to reality. Up there goes gravity. Now we get rid of the grams, and what we have is a certain number of moles, and the moles that I have is 0.005166 moles of the common ion or salt of the conjugate acid, so to speak. And now I want molarity, so I'm going to divide that by the volume, which has to be in liters. It's moles per liter when we talk about molarity, right? So I'm going to divide by 0.050 liters. And that's going to give me a concentration to be, I believe, 0.1033 molar. Okay, definitely going to get a point here for formula mass or converting to moles, and then we have the molarity. Now that's not my, basically that's what the answer is for I. They wanted the concentration of the ion. And again, the moles of this is equal to the moles of this. It's a 1-to-1 relationship. Of course, there's a sodium ion coming off there. But the ratio of this conjugate base ion and this salt are 1-to-1. So that's how that works. So that would be the answer, okay, for that. Now, the harder question is the next one. Captain, they want the concentration of H plus in the solution. Okay, so I'm going to write this value here, 0.1033 is equal to the concentration of the C3H5. I'm not sure what I'm doing there. H5 O2 negative, that's the conjugate base. Okay, so I'm going to get rid of this. And we can solve this two ways. I'm going to go with the equilibrium way. And we're going to go with the reaction here. What the reaction is, we have H, C3, H5, O2, equilibrium with its conjugate base, C3, H5, O2, negative, and of course the plus. Why the plus? Comes off in water. Now you can have water here, and this would be H3O plus. It wouldn't be any different. Okay. So here's initial, change, and at equilibrium. Well, what's initial? Well, as the question stated, we have a 0.265 molar solution. So there's just like the other question, it's sitting there, 0.265. Nothing's changed. We're going to assume none of this because none of this has dissociated yet. We're always in that theoretical position way above at 100% reacted before we get to any equilibrium. So we're going to start there. But here was 0 in the other place, but here is important to realize we have this concentration. We just added some of it. So the answer is we're going to add 0.1033. So we have some, so 0.1033. Okay. Now it's going to go forward because I'm at this position here. So it's going to be minus x, and this will be plus x and plus x. Why? Because they're all a coefficient of 1, as we've talked about. So at equilibrium, 0.265 minus x, 0.1033 plus x, and x plus 0 in your head is x. And of course, as we've talked about, we can approximate away this x, we approximate away these x's because compared to these numbers, these x's are tiny. So if you were to do that, you need a quadratic, if not more, and it would not change your answer. So we get them away. Now we don't get rid of this x, that's a value that's small that we want to answer, but these numbers are just so much bigger than the value of this would be because this reaction barely goes forward. It's got a low Ka. So now we solve for the concentration of H+. We're going to solve for x. How can I do that? Well, it's only one variable because when I plug this into the Ka expression, what is Ka? Ka is 1.34 times 10 to the negative 5. 1.34 times 10 to the negative 5. I feel like I got that wrong. No, trust myself. Is over the products. What's the products? Well, 0.1033 times x. All I'm doing is plug it into the equilibrium expression, all over 0.265. Products over reactants, Coefficients become exponents. And now we're going to solve for x. Okay, and so when you do that, you get 1.34 times 10 to the negative 5. You're going to divide by 0.1033, right? Just algebra. And then, of course, I times by the 0.265. And that gives me my value of x. And when I do all of that, okay, I get my concentration to be equal to 3.44 times 10 to the negative 5. And x is a molarity, right? It's a concentration. So that's the concentration of x, which, by the way, is H plus right here. We just found H plus. Okay, and that's the answer. All right. So no big deal. All right, and that's something you could have done that way. But my gosh, we have learned that what we just did here, party people, is we worked with a buffer. Now, what's a buffer? A buffer is a scenario where we have both a conjugate acid and the conjugate base. So what I'm showing you and making room here is to show you could have done this completely another way. And maybe you like this way, and it's nice to have different ways to do things. So what we need is the Henderson-Hasselbalch, which says that the pH equals the pKa plus the log of the conjugate base, okay? In this case, the conjugate base is C3H5O3 negative over the conjugate acid, which in this case it was HC3H5O2. And you say, well, why would I do it this way? Well, because once I solve my pH, all I got to do is do 10 to the negative x, because this is a log, to get my actual H plus concentration. Now you say, oh, Mr. Grodsky, well, you need the pKa. I don't think that's difficult. All I do to get the pKa is do what? Take this number and do the negative log. I don't think that's a big deal. Now, again, if you like the equilibrium and you go for it that way, be my host. There's no right or wrong way. So when I take the negative log of 1.34 and put that in my handy dandy calculator, I get a value that's equal to 4.87, and that's my pKa, which is an exponent. All right, so let's put that in, 4.87, okay, and now let's put the values in. What's nice about this, I can circumvent this table. I know the concentration of my conjugate what? Base. What is it? Well, this divided by that is what? Right here. So that's 0.1033. And I know the concentration of my acid is 0.265. So go find that number. So you go 0.1033, and you're going to divide by 0.265. So this number right here is just 0.3898, and just find the log of that number. Handy dandy calculator. And what you get, just rewriting this, so our pH is equal to the pKa, which we found to be 4.87, plus the log of this two numbers divided by, which these two numbers divided at 0.3898, put that, the log of that, and I get a negative 0.409. So when I add that together, positive 0.49 plus 4.87, I get a pH to be 4.46. Now they were looking for the H plus concentration, so all I got to do is 10 to the negative x there, so I would just clear that up. I go second function, 10 to the negative, I do second answer here for my calculator. And so what I get, my concentration of my H plus from the pH is equal to 3.46 times 10 to the negative 5. And all I'm showing you is that I can come to that conclusion using Henderson-Hasselbalch, which is using the buffer, how much of each of the acid and conjugate bases, or I could have came up with that using the what? These numbers are very similar and would be because they're answering it the same way. And the reason why they came out a little different, probably because of rounding here somewhere. So you decide which way you want to do it, but either one of the two ways is fine. So let's move on with this problem. All right, so we've got a new scenario here altogether. We have a new reaction. And look at this reaction. We have HCO2 negative with water, hanging out with water. It's equilibrium. It's not being driven. And here we have making some hydroxide ions. They want the value of Kb. Why is it Kb? Well, this thing must be pulling H's, accepting H's, not giving them off. Bronston-Lowry what? Bases accept H's. And we know that because going forward in the future, this must be the conjugate acid. This must be the conjugate base. This is acting as a base as an H+, because in the future, H2CO2 has one more H. And look what it produces hydroxides indirectly. So that's what bases do. So what's the value of Kb? All right, well, look what they give me. They gave me that the hydroxide is this in a certain solution. So you need to do an ice table, go ahead. CO, if you need to see it. Okay, some people do not because they're seeing what's going on here, but I will do it for you. We're still figuring this out. We're in our infant state here, plus hydroxide. Okay, let's put in the initial change in at equilibrium. And what do we have? Well, they said we initially have 0.309 molar of this. And you can think of, okay, initially, if I start with 100% of this, it's going to go forward a little bit, okay? And notice the amount of hydroxide is really small, so it goes forward a little bit. So it starts at 0, and this is going to be minus x, and this is plus x, and this is plus x. And if you see something, party people, wait a minute, they're giving me the hydroxide in this solution. So this thing is in solution, it reached equilibrium, and that's the value of the hydroxide. So that x that we're losing, party people, is that number, okay? Because that is the x, so this must be what? Minus, we're losing it, 4.18 times 10 to the negative 6, huge number. And this must be plus 4.18 times 10 to the negative 6, and this must be also plus 4.18 times 10 to the negative 6, running out of space. And of course, this is 0.309 minus that. But you can see how small that number is. So 0.309 minus that, well, we're gonna what? Get rid of that. It's insignificant. But these are my x's. So this plus this is that number. I'm not going to rewrite that. I was wondering if I would. And so to solve for Kb, which is an equilibrium value, it's equal to some, what, the products? Well, H2CO2 is what? 4.18 times 10 to the negative 6. And there's two of them. So I'm just going to square that baby. And it's all over 0.309. And again, if you want to subtract 4.18 times 10 to the negative 6 to that, you'll see that it's not going to significantly change that. All right? And then when you do that math, I get, party people, 5.65 times 10 to the negative 11. Booyah, okay? And that's pretty simple. Now, but they want the Ka for the conjugate acid. But what do we know? Ka times Kb equals Kw. So we have the Kw. We have the Kw, which is 10 to the negative 14. It's a constant. Temperature is not changing. We have the Ka. We just calculated 5.65 times 10 to the negative 11. And then we're going to find the K. Well, actually, that is the Kb, but we're going to times Ka equals that. So when you solve for Ka, it's equal to what? 10 to the negative 14 over 5.65 times 10 to the negative 11. So we put that in our handy dandy calculator, and we get 1.77 times 10 to the negative 4. And why does that work? Because a conjugate acid and conjugate bases do not really affect each other. As well as the acid goes is how poorly the base goes. They're inversely related. So if the forward reaction is more favored, then the reverse reaction is less favored, and so forth. So that's important. Okay, last little question. We're done here. Which acid is stronger, propanoic acid or methanoic acid? All right, well, propanoic acid is where you have, you think about it, propanoic acid, all right, and is this guy right here. Methanoic acid would be with 1 carbon, all right. Now, they don't really do they don't do organic chemistry anymore, but they could have drawn these. So propanoic, 1, 2, has 3 carbons. They would draw this out, and it would look like this. It's a carboxylic acid with 3 carbons. Methanoic acid, again, they would draw this out. Okay, would look like this. All right. Now, if you look at this carefully, when we talk about strength of acid, we're going to zoom into these bonds right here. There's an O and there's a bond between the O and the H. Stronger the acid means better the H can leave. So that these electrons, if they drift more to the oxygen end and move toward the molecule, this H can leave better to become an H+. So stronger the acid, the better these electrons drift. Okay, well, they both have 2 O's. But if you look at this chain in propanoic acid is more of a part of an electron cloud. If you look carefully, the longer this gets, the less polar this end gets. Because it's just an H here, this is more polar, right? Because this carbon chain has a cloud of electrons, but it's not as polar as this guy is. So the more polar it is, the more that these electrons will drift this way and easy for the electron to go. So you would say methanoic acid, okay, is the stronger acid with the higher, okay, Ka, because of more electron drift, because of more polarity. All right, that's how that works. Hope that helped.